Okay, so today I'm going to start relativistic quantum mechanics. Let me check sound. Hello. Okay, fine, it's working. Okay. So relativistic quantum mechanics. So far, what we have done is consider non-relativistic quantum mechanics, for which we know we did have a formulation, namely the Schrödinger theory, and we developed the path integral formulation, where the motivation was that to set up a question which could be asked in a relativistic context as well, though the answer to that question, so if we know how to ask the question which suits a relativistic formulation, then we will be able to find the answer as well. So that was the motivation. And so let us recall the path integral statement for non-relativistic quantum mechanics, and then try to see how the answer, where we should make modifications to answer the same question in relativistic quantum mechanics. So recall non-relativistic quantum mechanics, which I will call NRQM. In path integral language, in path integral formulation, there we had calculated, we had defined the matrix element and the overlap between final state and initial state, and it was given by integral dx from I to f exponential I over h bar s I f of x. This first of all, if we look at it closely, then we see that the non-relativistic nature is hidden in several places. This is the shorthand notation for xf tf xi ti, and however, this question itself can naturally be asked in a relativistic context. So this is also natural in relativistic context. Okay, because ultimately xiti is nothing but the initial event, and this is the final event. So this is an event. There is a genuine difference here, because these are non-relativistic paths, because these are given like x of t. Must be generalized. So I will come to that later. So this is something genuinely non-relativistic. This is also a non-relativistic action, because it is given by ti to tf dtl x dot and t. So this require genuine generalization. So we need to learn how to describe paths relativistically and how to find a relativistic action. We should keep in mind that this this action is something that under extremization produces classical equation of motion. So that should be a clue of how to do the same in the relativistic context. So therefore we should therefore for the in the relativistic context, relativistic quantum mechanics or RQM, for that the path integral statement will be if I given by integral dx I to f and then exponential I over h bar s if of x. But now this is xf xi. These are 4 coordinates. These are paths in Minkowski space. So therefore should be given by x0. So x mu of s instead of x vector of t. In the non-relativistic case, here both x vector and t should be included as the function. So mu equals 0 to 3. S is some internal parameterization. Because if you recall that, so this is say x vector and this is t, and this is a 4 space time, and there is a xi initial event and then there is a final event. Some path is there to final event, and we should have an internal parameterization, and we know, we are familiar from relativistic mechanics that an internal parameterization is proper time. Proper time is a good internal parameterization because it monotonically increases along path along path under time evolution, and is any reparameterization from tau. So ACE is equal to a function of tau such that it is this is also ACE is also monotonically increasing. So it is such that d tau is always positive. So it is called monotonically increasing function, monotonically increasing function. There is a more sophisticated name for it, which applies in higher dimension also, is orientation preserving diffeomorphism. So that's very sophisticated. Let's not go into this, but it is monotonically increasing function. S and tau are 1 to 1. Given a tau, there is a unique S. Given S, there is a unique tau. So those are that is another, just like proper time, such an S is also a good parameter, internal parameter. However, one should keep in mind that this internal parameterization is not physical, so it is unphysical. This is unphysical because, contrary to what happened in relativistic case, this argument, the parameter in the argument is a physical parameter. It had a physical interpretation, and which is not the case in the relativistic context. So in this case, in the non-relativistic case, x vector was a dynamical variable, t was a parameter, and when we wrote this, we were making a distinction between the dynamical variable, value of a dynamical variable, and the parameter that comes with the formulation, and which can be viewed as an artifact of the formulation. It is not a dynamical variable. The dynamical variable is x. However, the same thing, both x and t become the four coordinate x are the values of dynamical variable. There is no parameter does not appear here. So this since in the non-relativistic case, the parameter was a physical parameter, it did appear on a state, because it has a physical consequence, a physical interpretation, direct physical interpretation. So the states, though it's a parameter, the state dependent dependent on the value of that parameter, because the value of the parameter has a physical consequence. Here, the value of the parameter is, it's an internal parameterization. There is no physical consequence to that, and that does not appear in the specification of the states. When you ask the physical question, there is cannot appear directly, explicitly. Excuse me. And then your action must be action must have the form integral ds si to sf of some Lagrangian L, which should be function of x dot and s, where x dot is dx mu ds. Now, what guides us to find this Lagrangian? So this should be such, should reproduce classical equation of motion under first order variation. Okay, so that's the one more comment I should make here is that okay, fine, this is fine. So let me now, therefore, so okay, we now have an idea. So let me write down d tau, expression for d tau here. So d tau square is equal to minus eta mu nu dx mu dx nu between two infinitesimally close events. Eta mu nu is diagonal -1 +1 +1, and I'm taking the velocity of light c is equal to 1. Excellent. Now, it now remains to find out what action one should use. So let us look at the classical equation of motion. These are classical equations of motion are given by d tau is equal to 0, which is the massless case, and d2 x mu d tau 2 is equal to 0, which is the massive case. Okay. Now here is a geometric fact which is very important. Geometric fact is that these equations of motion extremize. These are extremization of these are okay. So these are geodesic equations. The classical equation of motion for the dynamical systems are also geodesic equations in that in geodesic equations in Minkowski space. Where what is a geodesic? Geodesic is a path given 2 points. Geodesic is a path of extreme length. Either it is a maximum or a minimum. So if it's a time-like trajectory, then the length, if the length is extremum, then of course the proper time should also be an extremum. So geodesic is the path of extreme proper time. Given given fixed endpoints. That means we could take the proper time itself as the integral of proper time, or the proper length itself as the action, because I should get these dynamical equations as a condition for extremizing the action. On the other hand, geometrically we know these are extremization of proper time or proper length, therefore action can be proper time. So this suggests that we could take action. So relativistic action is prime, I'm calling it prime, of x is equal to minus nu integral theta, which can also be written as minus mu integral ds from 0 to 1 Okay, so I have already explained what S is, and the boundary conditions are xi of S equal to 0 is xi and boundary conditions is x at S equal to 0 is xi, x at S equal to 1 is xf. So I have taken the what about the length, what about the parameterization S is, you can always scale the value of the range of S to be 0 to 1, and also show that the dimension of nu is of that of mass. Now, so this is okay. So action is proper time, proportional to proper time, and therefore and of course since it's extremized, since nu is an overall parameter, its extremization conditions will be independent of nu, and therefore nu is at the moment arbitrary. We don't know what nu is, and these equations are nu independent, and so that also fits with the fact that we could take action to be the proportional to the proper time. Now what the question that we have to answer is that how do we decide on this sign, minus sign? So the sign, overall sign, how do we fix it? The Euclidean action, so the corresponding Euclidean action will be given by S bar prime of x bar is given by minus I S of x, which is integral. So S prime, now you are doing a weak rotation, so minus and minus plus I nu, and then d tau is minus I du, right? Tau is equal to minus I u. That is our so this gives I square minus, so this is nu integral du, which is positive. So that fixes the sign, because Euclidean action should be positive. And so now let us check classical equations of motion from this action. Okay, so let us check classical equation of motion. This comes from a well-known. Okay, let's not bother about that. So delta S prime is equal to nu integral ds 0 to 1. So this is half minus eta rho sigma dx dot rho dx dot sigma to the power minus half, and then with an extra minus sign, so it will be 2 times eta mu x dot mu delta x dot mu with a factor of 2, because it's quadratic. So so this you can write as so this is dx nu dds. So this one is dds of delta x nu, which, and then with this dds you can do integration by parts because the boundary terms will vanish given the delta x vanishes at boundaries. You could write it as minus ds 0 to 1 dds of minus eta rho sigma x dot rho x dot sigma to the power minus half eta mu x dot mu delta x dot nu. We have used delta x nu at 0 equals delta x nu at 1 to be equal to 0. Variation at the boundary is 0. Now you can show that so now for arbitrary delta x nu, so if it is an extremum, you set this to 0 for arbitrary delta x nu.